It can actually hear, so everything you say, it can hear. So, just beware. Okay, so we're going to talk today about something called the fundamental theorem of line integrals. And here's kind of the point of this chapter. So when you had calculus with a single variable back in 241, you had a lot of really nice integral theorems. You had the mean value theorem for integrals, right? You had the fundamental theorem of calculus. And the sad fact is that a lot of those formulas don't go over to higher dimensions. So when we look at the multivariate forms of those, we see that they don't hold. So there is no general mean value theorem for integrals in higher dimensions, okay? And similarly, there's not a fundamental theorem of calculus. But what we're going to do is we're going to look at a special case where the fundamental theorem of calculus holds in higher dimensions. Now we're talking about vector value functions, right, that we're integrating. And I'm going to call it a special case because what I'm trying to say is that not all vector fields have this condition. However, it's not particularly special in the sense that in physics, a lot of functions will have this particular property that we're going to talk about today, okay? So it's special, but it's certainly not rare. So the starting point I want to begin at is the fundamental theorem of calculus. So everybody remembers that if I have a function of a single variable, this is a scalar function of one variable, and I integrate its derivative on some closed interval, this is the result I get, right? I get the antiderivative evaluating the endpoints. And I want to try to work towards something like that in higher dimensions, where now this is not a scalar function, this is a vector value function, okay? So let's think about what that should look like, all right? So I'm going to start off, and here's kind of the setting. We're going to have some sort of curve in 3 dimensions. It's going to go between 2 points, capital P to capital Q, and I'm going to give this a direction, okay? So these curves have directions. And this curve C is generally parameterized, right? So the way we think about contours is we think of them as being given by some vector value function. So I'm thinking of some position vector that's following along this curve as a function of time, that's some closed time interval, right? And typically we're going to say that this curve is smooth. And you probably remember from calculus, the previous calculus classes, smooth means that the derivative exists. It means that when you run your finger over it, you don't prick your finger or have to lift your finger. It's nice and smooth, okay? So the derivative of this function that parameterizes this curve exists. All right. And it turns out that if you want to get into technical details, everything we're going to say today, you can relax. We can make this piecewise smooth, okay? In other words, if I really want, I can think of a curve that has jaggedy parts to it, but I can break it down into subsections, right, where it's smooth, all right? That's what we mean by piecewise smooth. Kind of like a piecewise function, right? Except now the piecewise function is on the position vector that's describing the curve, all right? So given this sort of setting, okay, the analog of the fundamental theorem of calculus should look something like this in higher dimensions, right? So the equivalent of the derivative is the gradient function, right? It's just the derivative in higher dimensions, you can think of it. It's taking the dot product, okay, with the differential of the position vector, and I'm evaluating it between these 2 points. Now, just a really quick word about notation, okay, before we go any further. So people write contour integrals different ways, okay? Some people just write something like this, okay, where then they give C off to the side, okay? Since some people write contour integrals where they write the C here and the endpoints like I did there, I'm going to write it for reasons that will become apparent. I'm going to write my contour integrals this way, okay? Not necessarily standard notation. But this is what this should be in higher dimensions, right? If I have a vector value function, this is what I should be trying to do. And it turns out that there actually is a formula for this, okay? So we know what the fundamental theorem of calculus in one variable says, and what we want to know is this true? In other words, if we have the analog of this in higher dimensions, is this necessarily true? Okay. And the answer is yes. All right. So so this is kind of a special case of the fundamental theorem. Notice that this is not an arbitrary function. It's very important. This is not an arbitrary vector valued function. This is a vector. This is a vector field that can be expressed as the gradient of a scalar function, right? And that may not seem such a big deal, but that's a very strong condition. But it turns out that if we have something like this, yes, that holds. And the proof is actually very easy. I'll sketch out the proof just really quick for you. It's not particularly hard to do. But just to convince you this isn't a figment of my crazed imagination, right? So here's the proof that this is true. So I'm going to suppose that I have a vector function that can be expressed as a gradient of a scalar. And I'm just going to rewrite this. I'm just going to rewrite this inner product like this, right? Okay? If there's any part that I'm saying that doesn't make sense, just let me know, all right? And so I know that I can rewrite each of these differentials. X, y, and z are all functions of t, right? So I can rewrite this as, dx dt dt, dy dt dt, right? And dz dt dt. Oops. Okay. And I'm not going to get into the technical details. I just want to kind of flesh this out, but you can kind of see what's going to happen now when I substitute these back in. Okay, so I'm going to start at now. I'm going to make a change of variables. Okay, I'm going to now express this integral in terms of t. So I'm going from some time points a to b, and now this becomes partial of f with respect to x, dx dt dt. Plus partial of f with respect to y. Okay. Okay. And if you think about this carefully for a second, this basically ends up producing two. If you kind of use like a chain rule here, right? This ends up basically being this. I can write this as a total differential now. And now I really do have the fundamental theorem. Okay. And I won't go into the details of, we have partials here, we have regular derivatives here. I won't go into the details of that. You can go to the book and go through that. But this is the idea of why it should be true. All right? Just kind of a sketch of the proof. There are certain conditions we need on these functions. So these functions have to satisfy certain sort of continuity conditions. So if you go to the book, we go into those conditions. Generally, we don't worry about it. We don't come across functions that are particularly pathological, okay? But there are certain conditions regarding these functions that you do want to be aware of. Okay, so that's terrific. And it turns out that we can actually kind of state this formally. So this is theorem 2 in the book. And so this is no longer the fundamental theorem of calculus. That's really reserved for a single variable. Now this is called the fundamental theorem of line integrals. And the word integrals got chopped off here somehow. Okay. And so now we start to kind of get into technical conditions. So again, C is going to be some smooth curve, and it's given by some vector function. Again, f is going to be a differentiable function. It can be an R2 or R3. Okay, that doesn't matter. And the gradient is going to be continuous on this contour. So that's the technical condition, all right, that we have to have. And it turns out that when you satisfy this, you have this fundamental theorem. So this looks like the fundamental theorem of calculus in one dimension, right? That's what you would expect it to look like. So any questions about kind of what's going into the fundamental theorem, what we're trying to prove, any notation, anything that's not clear? Okay. Like I say, I'll send Professor Sprout the notes, so if you don't get all of it down, that's okay. Now, it turns out that this might not seem like such a big deal, and you know, fundamental theorem of calculus in one dimension is fundamentally different. Okay, it was of course nice to have, but it turns out in 3 dimensions this is actually a really nice thing, because the first thing we can say is that if I can get a vector field that's the gradient of some scalar function, it turns out this integral is path independent. All right. Notice that if you go back to this statement of the fundamental theorem for line integrals, right, the theorem says this. The theorem says I'm integrating along some curve from P to Q. Basically, this is what it says. And it says that this is f of q minus f of p. It's kind of another way of writing this, all right? Notice that there's no contour in here at all, okay? I'm just evaluating f at the endpoint, so there's no information about the contour. And that's exactly the point of this theorem. It says that this integral is path independent, meaning that if I think about those 2 points I had earlier, right, P and Q, so here's P and here's Q, and you can connect them using any path you want, okay? So, you know, maybe this is, you know, one path, okay? That integral using that path is going to be f of q minus f of p. This path, I'm going to get the same result, right? This path, and so on. And that's very useful in physics, okay? So we like this fact. And it turns out that there's even a nicer consequence of this. Notice that if I have a closed contour, right? In other words, if I think about a closed contour, so I start at a point, and what does closed mean? What do you think? Exactly, right. So if I have this contour right here, what should this integral be? 0. Exactly, right. Because I'm starting and ending at the same point. So this says, this is a very important consequence. We use this a great deal in electrodynamics. It says that this is 0. Okay. So these are 2 really important consequences of this fundamental theorem of line integrals, okay? Now, there's a really nice thing here going on. So a lot of times in mathematics, when we want to kind of look at a property different ways, we'll state equivalent conditions, okay? In other words, if one is true, the other is true. If the other is true, the one is true. If that makes any sense. So here it turns out that these 2 conditions are actually equivalent, okay? So this says that if every closed contour of some function is equal to 0, then it automatically follows that it's path independent for every contour, and the converse is true also. Okay. So this is path independent if and only if every closed contour is 0. And some people use. Have you come across this circle with a line integral? Have you done that yet? Okay. So this just means this is a notation. And if I don't know exactly what you've learned, okay, so tell me if you don't understand. This stands for a closed contour. This is a closed contour integral, okay? So this is a kind of common notation that people use. Okay. So sometimes people write C for an open contour and this little circle for a closed contour. Okay. So this is a really nice fact. But here's the problem. You're usually given a vector field. How do you know that it's the gradient of some scalar function? And that's kind of the import of what we want to look at today. In other words, yeah, this is all great, but it's all conditioned upon that vector function being a gradient, right? And that's not always true. Okay. So we want to know, given any old vector field, how do we know it's a gradient of a scalar function? Then we get all these nice things as a consequence, right? So we're going to start off defining this class of vector fields. So we're going to have this thing called a conservative vector field. And here's going to be our definition. So we're going to say let F be a vector field. And so F is going to map. And it doesn't really matter. It can be R2 or R3. Just, I'll just say R3, right? So it's going to map R3 to R3. Okay. And F is equal to the gradient of some scalar function, small f. Okay. So F is a function that takes a three-dimensional point and maps it to just a scalar. Work is like that, right? There's lots of things that are like that, okay, in physics. Potential energy is like that, okay? So F is a function that maps R3 to R2. I mean R1, sorry. Then F is said to be a conservative vector field. All right? And of course, the reason why we give this a special name is because it turns out that this is a really important class of functions and equations. How many people know what's going on here physically? Does anyone know what kind of physical background or context into? What's that? So we're going to be computing work, right? What do you think small f is? This is very interesting. Right. So what we want to do is we're going to use this to compute work. So what must this be? This has to be force, right? Force is the gradient of what? So think about it. Accelerations of vector.
It's the gradient of it and its velocity.
So we want to take a gradient of something that's going to be scalar value, right? So we know that it can't be acceleration, we know it can't be velocity, it's not going to be position, potential. Okay? So it turns out that this small f is going to be the potential function. So in real life applications, this is the context. So in real life context, this is a potential function. Okay. F, which is the minus gradient of the potential function, is the force, and that line integral is going to give us the work. So notice why we like this, because if we have these conservative functions, okay, you have these conservative vector fields, and we want to calculate the work, it says that we don't care what path you take. Okay? So this is going to be the idea. Not all forces follow this sort of behavior. Okay, if you have a force that's dissipated, you have frictional forces and stuff like that. When we're talking about these sorts of forces, we're talking about things associated with fields. We're not talking so much about mechanical force, right? We tend to have friction. And that's why these are called vector fields. So anything dealing with gravitation, electromagnetism, is going to fall into this category. All right. So, yeah.
So that you just think about gradient of.
Yeah, I should put a little hat above there. A little. And this is force. This is going to be equal to the force. Okay. And then the whole point of this is that when we go to integrate this, this is going to be the work along the path, the work done. Okay. Just like you did in Calc 1, way back in Chapter 6. Right? Questions? Oh, neat. Yeah, it is. It really is. It's really cool. And you see that this not only applies to classical mechanics, this also applies to quantum mechanics. So if you look at the Schrodinger equation actually has this exact same form. Okay, it's based off of this. So this is not just classical. Okay, so here's the big question: how do we know that? You know, we're given some vector function. How do we know if it's a conservative field? What do I have to show? So definition of conservative says what? It has to be the gradient of some function, right? So if this is conservative, as f is conservative, then f has to be expressed as the gradient of f. So what's my mission here? To find the scalar function, right? So I have to see if I can find such an f. Find the scalar function. Okay. All right. So how am I going to do that for this problem? Here's my function f. And the z component is x squared minus. How can I figure out if that's the gradient? What do you think? Any ideas? So a lot of times in math, how do we prove things? We start off saying, suppose it's true, right? And then we see if we get a contradiction, right? So if this is true, what does this have to be? If this is really equal to this? Right. Let's think about what the gradient is. This is the gradient, right? Or if we write it in this kind of vector notation, this is going to be partial of small f with respect to f, partial of small f with respect to y. Okay. So this thing here has to be what? Partial with respect to x, right? Okay. This has to be the partial with respect to y, the partial with respect to z. How am I gonna check that and see if that's true? Now sometimes people can just see these. A lot of differential and partial differential equations is being able to kind of see these sorts of correlationships. Some people can just see the answer, but suppose you can't. Okay, one at a time. Okay, what was this one? Okay, so just kind of slip on, yes?
Just say possible.
Possible. I don't think that would help. It would be great if it was that easy. Okay. Well, what would happen if I integrated this with respect to x? What should I get? Let's just think about this for a second, right? So if I integrate this with respect to x, let's go ahead and do that. I'm going to get 2xz dx.
Oh, and just make sure there's no responsibility?
I'm sorry?
And just make sure there's no responsibility?
So the smoothness really response really has to do with the contour, but the integrand doesn't have anything to do with that, right? So let's just kind of do this integral. So what do I know? I know that this is going to be, I'm going to get 2 times x squared over 2 times z plus, now my c, what is my c? Is it really a constant here? It's not quite a constant. Because f is what? F is a function of x, y, and z. So isn't this some function of y and z purely, right? So what do you want to call the function? Is phi okay? Everyone okay with phi and phi? Okay. So this is just going to be some function phi of y, z. Or in other words, this should look like x squared z plus some function phi of y, z. Okay. Now, if I took the partial with respect to x, I should get back my original component, right? Okay. So if there is such a function, it has this form, right? What about the y component? Can I do the same thing? Let's play the same game with the y component. I'm going to integrate the y component. So I'm taking minus 3eyz dy. I like integrating exponentials. They're very easy, right? We'll just get back the exponential. Z plus some different function. Oh, I don't know. Psi of xz. Okay. So f has to both be this and this. Okay. So let's just kind of write this up, okay, for a second. So we're saying that on the one hand, if everyone can see this, f of x, y, and z has to be minus 3e to the yz plus some function of x and z. But it also has to be equal to x squared z plus some other function of y and z. All right, this is kind of tedious, isn't it? I could do the same with the z component, right? All right. So what is it kind of looking like? What is it kind of looking like the answer is here? Maybe it's these two combined. That could be right. So let's go ahead and try that. So let's just say, okay, f maybe is this. Minus 3y squared, I'm sorry, minus 3e to the yz, and then plus x squared z. All right. What's the check on this? So I kind of cold-bloodedly set this up, right, so that this will give me the correct partials with respect to x and y, right? What if I try z? Let's go ahead and try z. So partial of f with respect to z has to be minus 3 ey, and of course that becomes 1, right, plus x squared. Is that what I have? Yeah, so this is not conservative. All right? Now here's the thing. Nobody wants to go through this, okay? This is really a pain. You have to find these integrating factors, right? You have to set them equal and figure out all this stuff, right? Yeah.
Over there, when you do the integral, isn't it z squared? Or is that?
Oh, I'm doing the integral, you mean right here? I'm doing the integral with respect to x, right? So z
I was
behaves.
just using the example on the board.
I'm sorry.
I guess you didn't write z squared down.
How did you combine it?
So I added them. So I said, okay, this is a function of y and z. This is a function of x and z. So let's see if we can get this to work out.
So that's wait.
Yeah, I'm not
Stream side.
I'm sorry. Oh, I'm sorry. You're right. Yeah, we should be. So let's see. So I don't think I should have a z squared here, right? But it won't change my final. It won't change the product, right? This will just be 6z here. Sorry, you're absolutely right. Sorry about that. But it still won't help. It still won't solve this problem. Okay. And if you wanted to, you could integrate with respect to z and check and see that you can't rather do that. Yeah.
So like negative 3 e to y z squared is equals to function of x, y, z. Then why don't you set the top and the bottom to get equal to each other instead of that?
You actually can. You can. And what you'll find out is that this has to be equal to this and that has to be equal to that. That's actually a good way of doing this, right? So I can set these two things equal and xz. And when you do, you'll actually come to the same conclusion, right? Right? This is kind of like how you do separation of variables, right? I bring everything over to this side, it has x and z, everything over here to f and g. All right, so here's the thing. We don't want to do this all the time. This is real pain. So how can we kind of get around that? So let's kind of take a look at this for a second. Let's be smart about this, okay? But just make sure, any questions before we go on? Everyone's good? Okay. So this is kind of really pedestrian, easy to do, but we don't want to go through this. So let's be smart about this, okay? So we're going to start off noticing something, all right? We're going to notice that, and I have some examples here that we could do kind of quickly, okay? Oh, my thing is not responding for some reason. What's going on? Okay. I have a Surface Pro, so that figures. Sorry. Okay. So here's the point that I want to make here, okay? So let's start off noticing the following, okay? If f is conservative, I'm going to put this if in capital letters. So if capital F is a conservative vector field, right? I noticed something really important. I noticed that these components have a relationship. And just for the moment, if you don't mind, I'm going to restrict myself to R2. Okay? So let's kind of break this up into two classes, if that's okay. I'm going to three-dimensional vector field and two-dimensional vector field. Okay? So here's how we're going to think about it. How do we know if that capital F is a conservative vector? Okay. And it turns out that the answer actually depends upon the dimension. Okay. So if I'm in R2, capital F has two components. Let me start off with the following observation. I'm going to say here, capital F is, so we want to have use CDF. Then we notice something. We notice that F can be written in this form. Of course, normally you're not going to be given that it's a partial, right? That's kind of wish that you knew that, right? So normally that's going to be written like this, right? Given some function, right? But the point is that if this is conservative, notice that the partial with respect to y has to be partial with respect to y, right? If this is really conservative, what I noticed that I know that because conservative means that Q is partial of some scalar with respect to F, partial with respect to Y. And because we're assuming that Q is here and partial so then that happens. Here's the problem. Notice to start off assuming that it's conservative. So we know we do a function with conservative, it's true. It doesn't help us. Right? It doesn't actually help us. So what we do really want, we might be able to find this here. Right? But if we're going to find this, how does it go back? So if this is true, then we can say that that's a conservative. This is such an important point. Let me just belabor this for 1 minute, okay? I'm going to continue this over here. So just to kind of be really clear what we're saying. So we're saying if capital F is a conservative vector field. This implies that, and I'm going to write it like this. Then this implies that the partial of Q with respect to Y is equal to the partial. Do I have it? Yeah, I have the right number. Okay, just want to make sure. Is equal to the. But we'd like to go backwards. This is called the converse, right? So what I want to know is is the converse true? In other words, if F has this form, and I'm not going to bother writing up, all of this, okay? And the partial of Q with respect to Y is equal to the partial of T with respect to X. Does this imply that F is a conservative vector field? That's what I would really like to know. Okay? And the answer is it does. Now, the answer is yes, but there's one condition we got to be careful about. Okay? Now this is the technical condition. So, is this true? I'm going to put a little question in here. Does this imply? And the answer is yes with a caveat. The caveat is that when we're doing these line integrals, okay, the domain that we're looking at has to be a simple closed region. Okay? I'm sorry, a simply connected region. The caveat is that F has to be defined on a simply connected region. So sometimes people call it a simply connected domain. That's the caveat. So what does that mean, simply connected domain? This is how the technical is. So this means that this is some sort of domain. Since we're talking about R2 here, we're talking about the plane. So this is what simply connected means. Simply connected, means we have some region in R2. Okay, I'm going to call this D. And what simply connected means that if you draw any closed contour, simply connected domain means that if you draw any closed contour, that's where the contour is contained in D, okay? It has to contain only points in D. So what do you mean by discontinuity? So that okay, so let me show you something that's simply connected and something that's not simply connected. This is simply connected because any simple curve I draw with points in this domain will only contain points in the domain. What could screw that up? No, the contour has to be in D. So the contour has to be in D. The point is that it only contains points in D. Right, so if you have, so here's an example of something that is not simply connected. Okay. This is one that is not simply connected. It has to be a single region, okay? If you have a domain that has holes in it, holes won't really throw you off, okay? It's actually what we call connected. So you can think of it, you can call it discontinuity, but really discontinuity is a function, really, right? So this continuity has some limits, right? Okay. So things when we have two regions that are disconnected, if we have regions that have Okay, so here's an example of something that is not so if I have something and I have a hole, I notice that I draw this close contour to the hole. Right? This is the close contour of my code, but it doesn't hold the same. So, the reason why you come across this, so like right now you may say, well, I never see that sort of thing. You might think of it because you think about it. Very often our case they're not totally pathological, okay? So this is a really nice result. So let's go ahead and summarize it. And I'll actually have so in R2 here, we're going to say that F is defined much easier. I much rather take derivatives than numbers. Right? Much easier. We can go back to that original example really quickly without talking about it. Good. If you want to, sure, go ahead. Yeah, just to convince you this isn't a figment of my crazy imagination. All right, so someone want to read it off to me? I have it in here somewhere, but you want to go ahead and just read it off to me? Huh? Now notice I'm going to have a hard time doing it for this one. Why? So what's the goal for R3? Actually, R3 says this. And I'm not going to get a chance to get into this a great deal, but I'll try to get into this one thing. So here's what the rule of R3 says. It says that the curl of the function is equal to 0. That's the rule. But when you look at that, and along with I could have actually used that. I could go to but this is just one thing. And if you think about it, this is actually equivalent to saying that the curl of 2. What does it mean for the curl on the function? Think about it. What does the curl look like? You guys talk about it. So here's the thing you like that here. So why do we care about all this now? Because conservative vector fields are radial. Okay? So if you have a conservative vector field gravitation is the same way. That big black hole. What is that? So the kernel, in a sense, is a relation of how much this vector is being driven. And certain events are not straight. So in a kind of very intuitive sort of sense, this is what we say. And what we say is we say this is relocation. We talk about relocation. These are all things connected. All right. Do you have any questions? Yeah. No, I think I'm not I keep calculus sometimes, so I can if you want me to go far next semester. I'm sorry? Yeah, it's a probability theory. If you're a double E, it's a little bit towards the half. All right, thanks for coming. I'll try to put this online. We'll see if the video took because my thing froze, and hopefully it did. And enjoy the rest of your weekend. All right.
I would like to know. Oh, okay.